This equation written in component wise is sigma aij aej xj equal f1 x1 xn j from 1 to n j from 1 to n anj xj fn x1 xn. Okay, so our ax equal fx is a compact form, vector form of this component-wise systems of n equation. Okay, with about n unknown variable x1, xn. So this equation is nonlinear. In linear algebra, we have studied the system of linear equation, and we have a complete solution about this problem. Whether there are solutions, and if there is some solutions, the structure of the set of solutions are clear for linear equation. But for nonlinear equation, this is a difficult problem. The first step is to establish the existence of solution. Now this is an example. Let's see how to solve this problem. Consider this function capital phi given by phi x is half of axx minus capital Fx. Then phi is C1. Okay, and since A is positive definite, so and alpha is less than 2, we have as x goes to infinity, we consider the behavior of phi x. Phi x is half of axx minus capital Fx. We apply the assumption on capital F, and because A is positive definite, this will be half of lambda 1 x norm square. Axx is not less than lambda 1 x norm square minus capital F. Capital F will not greater than the absolute value of capital F. It's not greater than alpha. Therefore, minus capital F will say minus say x alpha. But alpha is less than 2. So this term, the coefficient of this term, half of lambda 1 is positive because A is positive definite, so lambda 1 is positive. So this term grows, this term and the last term will goes to positive infinity. But this is a minus sign here. But because alpha is less than 2, so this term will overcome the last term. And it is easy to see that this converges to positive infinity. Now, phi is C1 function. Of course, it is continuous. And it is the limit of this function is positive infinity. Intuitively, Rn, the graph of this phi behave like this. So it must attempt a local minimizer, a global minimizer. So there exists a Cauchy in Rn such that capital phi Cauchy is minimum in Rn. Okay, this is true intuitively, but you need to prove this legally. You cannot depend on this graphical intuition. You need to the graphical intuition is helpful to motivate our idea, but once you observe something, you believe that is true, you must be able to prove your conclusion analytically. Okay, so this I leave you as an exercise. Okay, so we have a minimizer of phi, the global minimizer. Of course, this is global minimizer is also local minimizer because it satisfies more conditions. Okay, so by the Feynman theorem, we see that the gradient of capital phi at this point is 0, but phi is of this form. Phi is this function. I will compute the gradient in the next page. It turns out that this gradient is AXC minus the gradient of f, which is our AXC minus FXC. So AXC minus FXC is 0. This means AXC equals FXC, and this means that this minimizer point, this minimal point Xc is the solution of our nonlinear equation AX equals Fx. So this proves our conclusion that under our assumption here, this system of algebraic equation has at least one solution. So this proof has completed, but maybe you don't know how to compute the gradient of phi here. So I will show you how to compute. Actually, this is quite easy. Okay, just the compute by definition. So our phi x is half of AXX minus capital Fx. So if you want to compute the gradient of phi, you need to compute the partial derivative. Okay, so note that our small f is the gradient of capital F. Therefore, fi is in fact dif. Okay, so we compute the partial derivative of capital phi with respect to xi. Okay, obviously this is the derivative of linear combination is the linear combination of their derivative. Okay, so this is di half of AXX minus di capital Fx. So this is of course half of di AXX minus this is small fix. Okay, so we need to compute this. To compute this, we write AXX is the sum of aij xix. Maybe we don't use I because the I has been used in the here, so we use another index. Another index. So akj xkxj. Therefore, di axx is akj di xkxj, which by the product law is sigma akj dixk xj plus xk dixj. Okay, Okay, this is the product law. We use a useful notation dixk. If k is I, then the derivative is 1. Otherwise, it's 0. Therefore, this is delta ki. Delta ki clonic symbol means that if I equal to k, then it's 1. Otherwise, it's 0. So this is sigma akj delta ki xj plus xk delta ij. So because of this delta, we consider the first term. Because of this delta ik, here this aij term, only the term where k equal to I can survive. Other term is 0. So this is aij xj. This is the first term. Similarly, the second term is because delta ij here, only the term involving j, akj, only the term which j equal to I can survive. So this is aki xi. If the j here is not equal to I, then because delta ij is 0, so that term vanishes. So this is the sum j from 1 to n. Here is k from 1 to n. So this is because A is a symmetric metric. A is a symmetric. So aij maybe aki is aik. So we can write this by aik. So these two sums are the same, right? The difference is the summation index. The summation index here is j, but here is k. Otherwise, they are the same. In the second summation, you can replace the summation index k by another letter j. This will not change the sum. Therefore, this is twice of sigma j from 1 to n aij xj. So this is the derivative with respect to xi for axx. So we obtained the following result. Di phi x is sigma. The twice here is cancelled by the coefficient half in front of the computation. Okay, the 1/2 in the expression of di phi. Okay, so our conclusion is that j from 1 to n aij xj minus f I x. So together the gradient of phi x is, if we write the gradient in column vector, so this is d1 phi dn phi. So you will see that this is ax minus fx. Okay, so this proves our claim here that the bottom of this page, the gradient of phi is the gradient of phi xc is equal to a xc minus the gradient of capital F xc, which is small f xc. Okay, so this conclude this example. This example is very important. The method of setting solutions of some certain equations by looking for critical point in this example is minimal point. This idea is very powerful. and very useful in modern mathematical mathematics. This method is called variational method. For solving equation, in particular nonlinear equation. Okay.